Okay, so for the last talk of this session, we have Coraline Bogo, who will talk about their first graph traversal.
Okay, thank you so much for having me. This is the first time I present something, and this is actually my first paper that I did in collaboration with Wendell Duclos, Pekka Orponen, and Shiosuke Suki. So thank you so much for having me. I'm going to talk about a little problem that they have in molecular programming. So in molecular programming, one of their goals is to create nanostructure. So nano little 3D models that they can after that use in vivo or others. And to create such a structure, they use DNA and RNA, and they have this big machine that read the DNA and then produce some kind of RNA strand that will then fold itself into the structure. And they have a procedure to create such structure using DNA. So the goal of the work that we did was to study this procedure, determine which kind of 3D model can or cannot be done, and then analyze the restriction of it, and then have an FPT algorithm. So I'm going to present first the procedure to get such 3D model out of DNA. So the idea is, first, you create your template, your graph, that you view as a mathematical graph, and then you take a spanning tree of this graph. The spanning tree of this graph has the idea is that you create two double strands that will follow the path of this graph, once back and then forth. You attach for every edge that is missing, because of course the missing edge if you just take the spanning tree, you attach two half edges that are being called kissing loops. And then you can have your DNA sequence that will fold itself into this way. But there are two problems with this procedure that they managed to solve. The first problem is the fact that since the machine is quite large, it cannot go through a cycle of the graph. And so you must make sure that every cycle is closed and then never touched. And that is actually the case in DFS trees. So the first condition is that the spanning tree that we take is a DFS tree, so not this one. And the second condition is the fact that the number of those half edges of those kissing loops that they have is experimentally limited to 6. And so they cannot have as many as they want that are open at the same time. So once they have one first kissing loop and then another one that are open at the same time, they can have 2. And then one is closed, they can reopen it somewhere else in the graph. But they cannot have more than 6 open at the same time. And this is what led to the invention of the graph parameter called the KLX number, so for kissing loop crossing. So let's go through a formal definition of said number. So the idea is that you first take a graph, and then you take a spanning tree of this graph. So for example, here we have a graph G and then a spanning tree. What is important is that the procedure will go twice through each edge, once back and then forth. So you will have to order the children of every node from left to right, because they will first go on the left part and then on the right. Once you have your DFS tree, you take its linear order of the visited children. So for example, on this one we go from A, B, C, D, C, B. So A, B, C, D, C, B. And then for every single edge that is not present in the DFS tree, you create this kind of two half edges that will be open at the last time we see an edge. So for example, on D, you will open this half edge. And then once you are on B, you can close it. And so you create those kind of arc diagrams, this is how we call them, of the moment it's open and the moment it's closed. And the KLX number is, so the KLX number of a specific DFS ordered tree is just the number, the maximum number of those same time open arc diagrams, arcs. And then the KLX number of a graph is the best DFS tree that we can, the KLX of the best DFS tree. So the minimal out of all the DFS tree, ordered DFS tree of their KLX number. Let's go through a few examples. So first we're going to go back to the tetrahedron that we had previously. We can take a DFS tree of it since it's K4, there is only one DFS tree, it's a Hamiltonian path. And we can draw its arc diagram here. So for example, if we start here, we go from 1, 2, 3, 4, and then we go back 3, 2, 1. And then we can see at 4, for example, we open 2 package, then at 3 we open 1, and then at 2 we can close it. So this is at, open, and then close it at 2 and 1. Another example that is maybe more interesting, because this one has only one DFS tree, is the cube. So the cube has two different DFS tree. The first one is the Hamiltonian path that go through every single vertex. This one has a KLX number of 4, present either maximized here or here, and of course all the Hamiltonian paths are the same up to permutation. And the second DFS tree is some kind of split, where you try to split the cube into 2 different components using your path. And this one actually has the worst KLX number, because those 2 back edges are actually now kind of on the same place. And so the KLX number of the cube here will be 4, obtained with this DFS tree. Okay, now that we know what the KLX number is, can we find some properties of the KLX number, and can we compute it? That is the 2 main questions. So there are a few links. First, there is a link with K-connectedness that we already defined in the previous talk. So just as a reminder, the K-connectedness of a graph is the number of vertices that you can remove such that the graph stays connected. And the first parameter that you can see is the fact that if you take the maximal 2 connected component of the graph, so those blocks, then the KLX of this component, of this subgraph, is actually less or equal to the KLX of the whole graph. The reason is, if we have a DFS minimal tree of the whole graph, and then we restrict it to only this component, then we know that it is also a DFS tree of that subcomponent, because the tree cannot escape and re-enter. Otherwise it would be not maximal 2 connected component. Since it cannot escape and re-enter, it is also a DFS tree of that component. And then the KLX number is bounded by the KLX of the whole graph. Another link with K-connectedness is the K-connectedness lemma that just states that on a B-connected component, if you take a look at the K-connectedness, then the KLX number is at least K minus 2. And I'm not going to prove this one, of course it's in the paper. Using those 2 lemmas, we can already have a proof of a characterization of KLX equal 1. So it's something. So let's go through. The characterization of KLX equal 1 is the fact that a graph at KLX equal 1 if it is a cactus graph. If and only if it is a cactus graph. So just as an example, as a reminder, a cactus graph is a graph where it can have cycles, but the cycle cannot have edge-touching parts. So they are all distinct in edges. They can only touch at vertices, but not at edges. So one way of this proof, of this characterization, is already done by the above lemmas. And the other way, well, we just need to find a good KLX tree, a KLX DFS tree, to then prove that this one has KLX1, all cactus graph has KLX1. And so how can we do that? We pick any starting point in our graph, and then as long as we are in a cycle, we will prioritize to visit exterior, like outgoing edges from the cycle. So for example, we start on the cycle, we go through the cycle, and as soon as we see a point, then we'll prioritize to exit the cycle. So we exit and then re-enter the cycle and then continue. We haven't opened any edges yet. Here we encounter again another exit point to our current cycle, so we exit, and then we do the same. We arrive here, and here we cannot go here because it's a DFS tree. We already visited that zone, so we are going to open it. But since we visited every single external edges on our way back, we're going to open it and then close it immediately as soon as we re-enter from the other side. And so we keep doing that, and we get a DFS tree that have KLX1 for any cactus graph. That's good. We have a characterization for KLX1. Can we get better? Can we compute it? Unfortunately, I mean, I'm pretty sure you saw it coming. Computing the KLX number is NP hard. This is by reduction from min cut. And since it has been introduced last year, it's quite recent. But we are not satisfied enough with that answer. We want to know if the testing the KLX number, and that is actually the biological need. We want to test if a graph can be made using this technique, because we only have a finite amount of kissing loops. We want to know if this is in P or if this even better, FPT. And so our result, three main results. The first is that we have an explicit algorithm that can be actually used for KLX less or equal to 2. I'm not going to talk about that much in details. But you can come see our group to talk about it. I'm just going to outline the main idea. And then, using MSO2 and Courcell's theorem, we can have a proof that testing if the KLX number is less or equal to k is actually polynomial for every k. And even better, we can actually generalize this to say that it is FPT. Okay, just a rapid summary of the KLX equal to 2 proof. So, this is the main idea. The idea is that if we have a KLX equal to 2 graph, we can decompose it into some sort of ladder pattern that can look like this, in which we have two zigzagging patterns that go through every single graph. Those are edges and those are kind of paths. But the black edges can contain simple cycles that are disjoint. So the black edges are kind of cactus graph in a way. And the red edges can only be paths. And the idea is that here we have one more KLX that we can use, one more open edge that we can use, and on this one we have not because there is one open here and we need to close it here. So this is a decomposition, and you can read the paper if you want to know more about it. I think the main key takeaways are on the MSO part. So this is what I'm going to talk about. If we want to have some kind of polynomial time algorithm or FPT algorithm using MSO, a good starting point is to find links with tree width. Because of course, MSO works only on graph of bounded tree width. So can we, for example, bound the KLX number by the tree width? And the answer is yes. This is the theorem that we proved, the fact that for every graph, the tree width is less or equal to KLX plus 1. For those that know very well tree width, you might be a little bit surprised that the plus 1 is here and not here, but it's actually, there is a reason for it. And I'm going to give you an example for why this is true, using a simple DFS tree. The idea is that if we take a DFS decomposition of G that has minimal KLX number, and for example this one, we can try to get some sort of line graph of this DFS tree. So for every single edge that we have, we're going to create a node, and we order them by their top to bottom ancestor parent relation. And then the idea is that for every edge we have a node here. So for example, ED gets this node, and then CD and CF are both children of the BC edge, because everything is ordered. And then this will give us our tree decomposition, and then we need to fill the sets of the tree decomposition. And to do that, we are just going to use the open moment. For example, D in the KLX traversal, D will be open at this point and close when we reach again A. So we're just going to add D into all of the vertices, all of the bags in which it is open during the traversal. Because there is not more than KLX open edges at any time, every set only contains 2 vertices plus KLX elements. So 2 plus KLX, and so 1 plus 3 width, because 3 width has an offset by 1. So this is a very good thing, because now that we know that the KLX number bounds the tree width, then we know that to test if a graph has a low KLX number, we can just apply Courcell's algorithm because now we have bounded through it. So let's see how we do the MSO translation. So how to encode the KLX number using an MSO formula. Well, it's a little bit, we have a little bit of an issue. Because the KLX number depends on the order in which we visit the children. For example, if we start visiting this tree from left to right, we're going to open D and then at the same time open F. But if we order them from right to left, we're going to open F and then close it before opening D and then close it. So on one side the KLX number is 2 and on the other the KLX number is 1. So it depends on the order of which we encode the DFS tree, and that is kind of a problem because on MSO, encoding a full ordering of the children on every single vertex is not really possible because this is an unbounded amount of information and this is not a proof, of course, but morally it's going to be very, very hard. So how can we solve this? Well, lucky for us, there is a little theorem that we can use. A little theorem that states that if we take a DFS tree that have those kind of ordering, we can actually push all the interesting edges to the end of the ordering. And we only need to store the ordering of the KLX last children. And so this is just an example. If, for example, when we have a U with children V1 to V5, and for example V4 and V5 have back edges that are open, since we know that there is less than KLX number of them, we can all push them to the end and then encode an ordering on the KLX last children. Since KLX is a fixed value for our formula, we can just encode them using sets, C1, C2, C3, to order them, to give an ordering of the different last KLX children, and then we can just encode it, and we have to morally add to the formula the fact that they cannot have any back edges from any of those other V. And then we're done. So, what does the final MSO translation looks like? Well, first step, as we stated, is to encode first a DFS tree and then an ordering using sets on every single children of at least K of their children. We don't need to store every single one of them, just the last K. Then we need to create a formula that states that a back edge, that takes as input a back edge, and then returns all the position in the DFS tree in which this back edge is open. This is also doable. We just need a small little lemma on the equivalence way to restate this ordering, but it's not that hard. And then we take a cover of all edges that can have, it's not a partition, you can actually have the same edge in multiple places. You take a cover of all the edges of the DFS tree that will, in a way, allow you to really encode for each back edge the moment where it's open. The key thing is that this cover has only K sets. And then you just have to verify that every single open moment, open back edges, perfectly maps to this cover of the sets exactly once, and there is also a way to say, oh, this part of the cover is for this back edge. And so we just have to test that the set of all open back edges and the moments where they are open create a perfect disjoint spanning of all of those VK. And now, since there are only K sets, well, we know that the number for every given edges, we know that the number of back edges that are being opened is at most K. So this is the main idea. And we can actually generalize this to FPT because we have that boundedness. And the size of this formula is actually polynomial in K. So we can just generalize it to FPT. What are the key takeaway from this, other than the molecular programming is awesome? The first is, of course, the results. So first, there is an explicit algorithm for KLX 0, 1, and 2. 0 being just trees, so very interesting. There is a way to test if the KLX is less or equal to than a constant in polynomial time, but the algorithm is not really usable in practice, but it exists, so maybe one day we'll find it. And of course there is also an FPT algorithm to compute the KLX number parameterized by the solution. So of course there are two big open questions when we have results like this. The first one is can we actually make it usable? Can we actually compute it with a more efficient algorithm than the Quasar algorithm that give us a huge constant in front of the KLX number? And the second big open question is how does this graph parameter relate to other graph parameters? We have also proven that this has not yet been published, but we also have proven links with cut width and so on. So we are guessing that there are other links to other graph parameters, but we have yet to find that. Okay. I went a little bit perfect, so thanks for listening.
Any question? So actually I'm curious. So can you also bound the KLX number by the tree width from above?
We have found a counterexample of a series parallel graph with unbounded KLX number. So there is this. It's not in the paper, but there is this counterexample that you can define inductively of a graph that is series parallel, so tree width 1 or 2, and that have unbounded KLX number for hard to explain reasons, but it's kind of it has a nice inductive definition.
Yeah. Nice. So actually, this is quite similar to cut width, right? So I think the only difference is that you don't for cut width. I think there's no you don't need to follow a DF DFS tree, right? That's the only difference.
Yes, there are links. There are big links with cut width. For example, I need to make sure the multiplication is the correct side, but I think the cut width is less or equal than the KLX times the degree of the graph.
Oh. Okay.
But unfortunately, finding upper bound is really hard because DFS trees are really hard. But we do have a bad upper bound using cycles. If there are too many cycles, a little bit of everywhere, then there is an upper bound in the KLX number. Not that usable one.
So in the last slide regarding the open questions, in the open questions you mentioned about explicit algorithm for testing KLX, but you also mentioned earlier that it is already NP hard. I mean, then it is.
Yeah. So computing the KLX number is NP hard, but for fixed K, testing it.
Yeah, that
still
you already proved it is FPT, right?
Yes.
You proved that it is FPT, but finding like in absolute P will be very difficult, right, for testing.
You can, well, our guess is that using a tree decomposition of the graph, you can probably make some kind of dynamical programming that have.
What I'm saying is like if you can test it in P, then you can just test the values from 1 to n, and then like the whole thing will be in P. Like computation can also be done in P. So unless P equals to NP, it is not expected that you can.
No,
test.
computing it is NP hard.
Yeah. So I'm
Testing it is P, but the algorithm that we have is not usable because it has a huge constant. Because of course, as algorithm.
Yeah, I'm not. Your algorithm is FPT, but I'm saying, okay, I mean your algorithm is FPT, but I'm saying that you cannot do anything better than that. I mean you cannot make it absolute P, and that's what I'm saying.
Yes, yeah, of course. You cannot compute the KLX number in polynomial time.
Yeah.
Unless P equal NP. Yes, of course.
Hey, sorry, maybe
What
you can
you-
show the last slide. Okay,
Yeah.
what was the
So when you mention in the open question, like can we find an explicit algorithm for testing the KLX number?
Testing.
What I'm saying is it is very unlikely to do that.
No, we already have a polynomial testing. So for a fixed constant, testing if it is less or equal.
Yeah, then it is not an open question. Like you already gave an FPD algorithm for that.
Yeah, but it's not that explicit. Because it's
like
not
the
okay.
constructive?
Maybe I should have used usable, but I don't consider a
Oh,
Courcelle
also
space
maybe
that way.
like
What is the
very
difference
explicit.
between your algorithm and like your algorithm is FPD, but why it is not explicit? I mean,
without using Courcelle, you mean?
for
like a
constant
common-
values it will work, right?
So what do you mean by explicit algorithm?
I mean, just like for KLX less or equal to 2, for example. So an algorithm that is not using Courcelle's theorem, that we can actually implement in practice and doesn't have a huge constant in front of it. So I guess it's more of an engineering question, if you want,
Oh.
of can we find an algorithm that have,
Which is more practical.
yes, that is actually usable, that we can actually
So what
use.
is the exact bound for your algorithm? So suppose KLX number is k, then what is the time complexity of your algorithm in terms of k?
Of this MSO based one?
Yeah.
Depends mainly on the complexity of the tree-weak decomposition that you're going to use to get
And for
tree-weak.
you are using the Furcher's theorem or something.
But well, it's basically the complexity of Courcelle's theorem.
Yeah, I see.
Okay, maybe we can continue offline.
Yeah.
But let's thank Caroline again. And